Hi, and welcome to Allen High School's discussion of atomic structure at the APIB HL level. Now, when we're looking at the structure of a substance, it can help us understand how to develop or answer really cool questions, because at the heart of chemistry is that structure determines function. So if we can understand the structure of an atom, we can start to answer questions like, how do we develop a new computer chip with smaller geometries, faster speeds? What would be the best chemical for reducing all these wrinkles your little old lady teacher has been getting? You may want to go out and get a tan, and I'm going to caution you about skin cancer. So we'll need some chemistry to help us tan safely that doesn't make you turn orange in the process. Now, in order to focus on that, what we want to look at is Coulomb's law. Coulomb's law, you will see crop up. It's kind of like Where's Waldo throughout our conversation. Coulomb's law is going to crop up all semester in a whole variety of contexts. Now, life, whether you fall in love, what jobs you like, and the chemistry in your world is all about attractive and repulsive forces. So according to Coulomb's law, if Q is positive, if Q1 is positive and Q2 is negative, we will have a negative potential energy. And that's a good thing. Negative potential energies in chemistry means it's a more stable situation typically. Now, if we have, on the other hand, either positive or negative and negative, then what that's going to do is make our potential energy positive. That will be repulsive forces. And then you notice that the closer charges get to one another, the greater the attraction or the greater the repulsion. And we will often substitute R in there for distance. Now, we're going to be using this much more qualitatively than we will quantitatively over the next semester. And we'll be talking about fully positive or fully negative charges, like in this unit when we talk about electrons and protons. But later on, especially when we get into bonding, we will use it to talk about cations and anions. Now, in a number of chapters, I don't remember which in my book, my elusive little electron book, we'll talk about partially positive and partially negative. Coulomb's law still applies, particularly in a qualitative sense. And in fact, not only are we going to talk about partial, that's you start writing a figure 8 and stop before you kind of cross over the boundary there. We'll also talk about temporary. And what I like to do with those is use dotted lines. And we'll have temporary positive and temporarily negative charges. And Coulomb's law is going to apply to all of these. So that's a theme that I want you to kind of be tracking as we go through these. Oops, sorry. Let me get my... Now, let's take a look. What I have here is I have what I call the wheel o' dead guys. It's there for your reference. Really, the core thing that I want you to see here is the progression of models. And I'll just put up a quick review of these models, but I want you to note the progression of models, that models are not static. They're not once and done. Models in science, and it's going to be, again, a theme that's at the heart of our conversation this semester. Models are dynamic, and they're open to changing. A model is simply our best representation of our current understanding of a phenomenon. And as new experiments are done, we may need to pitch a model or refine a model. And I think atomic history gives you a good idea of how that is done. And we can model things in a variety of ways. We'll see things modeled using mathematics. We're going to see particulate representation. We can model our understandings using graphs. So we'll graph things, and that's going to help us understand, the effects of kinetic energy on temperature, for example. Or in this case, this might be changes in volume with temperature, if you remember your gas laws. We will use all sorts of other kind of pictures to help model our understanding of chemistry. Chemical formulas I consider a model of the abstract, that which we cannot see readily, so we have to have a way to describe it. And this Wheel of Dead guys, I wish we had time for that. Unfortunately, that's something we don't have a lot of time for, but I wanted to give you just a glimpse into that kind of process that we have in the thinking that went on. And also notice that there's a lovely little dead woman in there, although some would not call Madame Curie lovely. All right, so our model is a way to describe our understanding of truth, our knowledge of truth. Now, this is a case where you've seen most of this in pre-AP, so I'm going to run through this. You can pause, fill in your blanks. I expect you to know this. I wanted to give you a framework. You do not need to know all of this by name and date. We're looking at the big picture of how models evolved over time. John Dalton, he's often considered kind of the father of atomic theory, but he thought of more of a billiard ball. He, came up with a number of proposals, some of which we now know are false, and some which were shown to be true, which is pretty cool because this was a long time ago. And he came up with some direction for the next level of experimentation. The next one I want to focus in is Thomson. Thomson did this cathode ray experiment. You saw this in pre-AP chemistry. He discovered really that there is a negatively charged particle within atoms. And since you can produce electrons, that's a way we're not going to get into, but you can produce an electron stream. Well, much like what we'll talk about later on when we talk about photoelectron spectroscopy, electrons were attracted to the positive plate. And so if you look up here at my cursor, right here, you have a positive plate and electrons were attracted to that. So he came up with a true proposal, and then he drew a model which turned out to be false. So Rutherford did an experiment, and I have a wonderful animation. Please remind me to play that, or at least give you the link to play it while we're working in class. Using, alpha particles, he discovered that Thomson's model was incorrect. And based on these results, and again, you don't have to memorize these dead guys. This is a quick overview review of some things that we did in pre-AP chemistry. I want you to get at the heart of the models. Now, what was key about Rutherford's model, so go ahead and fill in your true and falses, is that he discovered that an atom is mostly space. So if you put a football in the middle of a football field, that's going to be the nucleus, and all the rest of the football stadium, including the stands and everything, would be what I like to call the electron playground. Millikan then went on and found the magnitude of the charge of an electron. So you see the progression of models, and it's okay that people are wrong. What the goal is that the model spurs further investigation. All right. This is Bohr's model. We're going to spend a lot of time talking about energy levels on this. You want to make sure you understand his good stuff. And then the bulk of our time is going to be spent talking about Schrödinger and Schrödinger's model and how that helped us launch our current understanding of atomic structure, which is the quantum mechanical model of the atom. Now, I know that was really, really quick, but I want us to move on. And so in our next video, we will review some of the components of an atom. In fact, I'm just going to do that now. Go ahead and pause, get those blanks filled in. For your electrons, we've talked about this earlier last unit when we reviewed naming. So go ahead, fill in your blanks on that. your neutrons. This is verbatim out of the pre-AP notes. So this should all be review. Now in our next unit, what I'm going to do is land here on isotopes and how to, just to refresh your memory on how to perform calculations to determine the atomic mass. This shouldn't say atomic number there. This should say atomic mass. I'm sorry about that. On the periodic table is a weighted average of the different isotopes. So that, wow, is a very rushed, I did not want to waste your time on this, a very rushed discussion of the basics of the atom and atomic history. I don't know if you can do the dead guys much faster. So until our next video, this is signing off.